Yeah, sure. Let's go.
Okay, welcome everyone. So this morning we'll start with a talk by Marcos Marinho. He'll give his last talk. Please.
Okay. Well, thank you very much. So let me remind you the lessons from yesterday. And the main lesson is that in quantum mechanics, Borel singularities are due to instantons. Okay. At this, okay, actually I should qualify this. I would say in 1D quantum mechanics, Borel singularities in Borel transforms are due to instantons. Okay. And so this is the first thing. The second thing is that the factorial growth of the ANs is due to the proliferation of Feynman diagrams. Okay. Actually, resurgent techniques allow you to get very good estimates of the growth of Feynman diagrams. So in order to clarify this, let me actually look at again at the quartic integral. So we saw that this integral was asymptotic to a series phi of g. And actually, it's very easy to get a diagrammatic interpretation of this integral. So as usual, it's good to go to the connected. So if you want to get a diagrammatic interpretation, it's better to go to connected diagram. So you take the log. And then if you take the log here, well, you will find, let me just make sure that I get the conventions correct from here. So you get minus 3/4 over g plus g plus, where are these right here? Should be written somewhere. Well, anyway, so let me try to get it from here. Plus 3 plus 12. 1 plus 3. Plus 3, 4. Plus 3, I think it's 3g cubed, 3g squared, and so on. And actually, you can see that this you can obtain by counting diagrams. This corresponds to this diagram here. So, you know, these are diagrams. These are connected vacuum diagrams in a lambda 5/4 theory. So you get, from this term, you get this. From this term, you get two possible diagrams. So these are diagrams, connected vacuum diagrams with two vertices. So you get this and so on. So you can actually see that the ANs are actually counting connected vacuum diagrams. And of course, what we saw is that Fg, the coefficients of phi g, grow factorially, but it's also easy to see that this doesn't change when you take the connected part. So the diagrams, when you take the log, are also growing factorially, and of course, once you exponentiate, this remains the case. So both connected and disconnected diagrams grow factorial. So it's interesting also that, you know, going to connected diagrams doesn't decrease the number of diagrams radically. This is something sort of counterintuitive. You would think that, you know, maybe by going to connected diagrams you would reduce the growth, but not. Both connected and disconnected grow factorially. And this is the source of the factorials that you see in this type of calculations in quantum mechanics. Now, of course, if you go to this is for the quartic integral, but actually you go to one-dimensional quantum mechanics, the counting of graphs is the same. So what you can see in quantum mechanics is that, you know, so a term is essentially Feynman. So you have Feynman diagram plus Feynman integrals, right? So there are two things that you have to be careful in calculating a diagram. So when you calculate the diagram, you will have a number of terms. Each term is given by a Feynman integral. So if the number of terms grow factorially, then this thing grows factorially, the total thing grows factorially, but you also have to be careful about how the Feynman integrals grow, okay? And the Feynman integrals grow only exponentially. So this means that all factorial growth comes from this. And as I said, you can check this in much detail. So Bender and Wu did this check in detail. Check this in the quartic oscillator, okay? And this is important that I make this distinction between the counting of Feynman diagrams and then the fact that each Feynman diagram is being by an integral, because we will see that in quantum field theory, things are more complicated, and it turns out that even the Feynman integrals can grow factorially. And this will lead to a new source of growth, of factorial growth in quantum field theory, which is not seen in quantum mechanics. So, and this is in a sense one of the most important differences between quantum field theory and quantum mechanics. In quantum mechanics, is the number of diagrams that grow factorially, but the Feynman integrals, as you increase the number of loops, when you calculate a Feynman integral, you have to integrate over the number of loops, you have to integrate momenta, and it turns out that with the number of loops, with the number of loops, Feynman integrals only grow exponentially. But this is in quantum mechanics. In quantum field theory, there are examples, many actually, this is the default situation in which the Feynman integrals themselves can grow factorially. And this gives a new source of factorial growth in quantum field theory, which is not present in quantum mechanics. So it's not true that quantum mechanics, the quantum field theory is just a simple generalization of quantum mechanics. There are going to be qualitative differences, okay? And I will comment on this today. Okay, so this is the first thing. Now, another thing which is interesting is how you put together resurgence and the 1 over n expansion. And this is actually conceptually and practically important, because you could say, well, right now we did all the calculations with a fixed capping constant and so on. What happens if you start like playing with n? If you have an n variable, a large n variable in your quantum physics, this could be the number of flavors, the number of colors, and so on. What happens? Okay, and we will see that this is also very important. And it will give us, again, a new criterion to take into account in quantum field theory. But what I'm going to do is actually something very simple, which I find a very good exercise, which is to do large n limit in conventional integrals. Okay, so we're going to take the quartic integral, and we're going to see what happens when you do a large n generalization. Okay, so I'm going to define a sort of large n, well, finite n generalization of my integral. So I just take, you see, my original quartic integral was in 1 dimension, so I'm going to do it now in n dimensions. So, so I just do this. So now x is a vector of n components. And I just generalize this to an n-dimensional integral. And let me point out that there is a beautiful article by Brezan and Ikami where they do this sort of analysis. Okay. Now this doesn't actually change much the situation. So before we were remember that the perturbative series for this integral was obtained by doing the expansion on the trivial saddle point. Now we could do an expansion again around the non-trivial saddle point. And we will get the finite n generalization of this thing. And then you see what happens now is that all coefficients are functions of n. So g to the n. And you can actually write these coefficients in closed form, because you can by using spherical coordinates, since this integral has a spherical symmetry, you can essentially reduce this to a 1-dimensional integral, but there will be an independence. So you get -1 to the k, then gamma of 2k plus n over 2 divided by k factorial gamma of n over 2. Okay? So now, if you actually take the log of this, well, before getting the log, let me just point out that this still grows factorially. So for a fixed n, for a finite fixed n, this still grows factorially, and you have this essentially slightly different story. So you have a slightly different growth, and you can do the same game as before. You can now do a saddle point approximation around the non-trivial saddle. There is something very interesting here, because what is going on now is that there is a family, a continuous family of saddle points here because of the ON symmetry. So you have to be a little bit careful. You have to introduce collective coordinates and so on, and zero modes and so on. But you can reproduce everything. So doing this calculation for finite fixed n is just a straightforward generalization. Yes, do you have a question? Yes? Yeah, it determines the nature of the branch cut. Yeah, yeah. Yeah. This. Of course, this is up to. This is modulo 1. So essentially, this is going to. So the is modulo 1. Yeah. Because you see, when you have a branch cut z to the minus b, if b is bigger than 1, you see, 3/2 is like 1/2 from the point of view of branch cuts, right? So this is essentially modulo 1. Yeah. So it doesn't really change so much. Okay. Very good. So now, but now what we want to do, so this is finite n, but we want to do the top limit. Yes? Oh, yeah, that's true. Absolutely. Absolutely. Thanks for being so careful. E to the k. Absolutely. Sorry. So what we want to do is the top limit. So the top limit is very different, because we want to take g. We want to take limits in which g goes to 0, n goes to infinity, and we want to fix the top coupling L lambda is the top coupling. Okay. So here the story is very different. So let me actually see what happens when you do this. So if you calculate this quantity here, 1 over n log phi over n of g, which is just the contribution of connected diagrams to this large n integral, you will get this type of terms here. So you get this generalization, n plus 2 plus n plus 3 over 4. This is kind of a very easy calculation that you can do. But now, in the top limit, you want to actually isolate. You see, this quantity here, this is A1, this is A2. So A1, A2, A3, and so on grow factorially. But now, in the top limit, you want to write this in a slightly different way. You want to write this as a large n expansion. So you're going to get functions of lambda with n to the minus lambda, n to the minus L. So what you could call the large n limit, or the planar limit in this case, is just the function f0 of lambda. Okay. Now it's very easy to actually calculate f0 of lambda here, because what you do is actually to isolate the higher powers of n in the coefficients. Okay. You see, that's where n times g is lambda. N squared and g squared is lambda squared. So by isolating these pieces of the coefficients, you get the large n limit of this quantity. But notice that out of this number, which is ak, you are selecting a piece. So it's not longer obvious that this selection inside ak, inside this factorially divergent coefficient, is going to also grow factorially. This is not obvious. So let me just continue. And so you can actually compute f0 of lambda in this way, and you get minus lambda over 4 plus lambda 4 over 4 minus 5 phi lambda over 12 plus so on. And the question is this series divergent? Is the series factorially divergent? And the answer is no. This series is no longer factorially divergent. Okay? This series is actually, so the answer is no. So actually phi 0 of lambda has a finite radius of convergence. And the reason is also, you can also understand this diagrammatically. What happens is when you do the large n limit, out of all these diagrams that grow factorially, you actually select a subset. And this is the subset of diagrams which grow, which leads to a fixed power of n. And it's known diagrammatically that this set of diagrams only grows exponentially. Okay? So this is a crucial aspect of the large n limit. Here I'm doing it in a very toy model, which is this quartet integral, but this turns out to be true for essentially all the large n limits that you are used to. It's true for vector large n limits, and it's also true for matrix large n limit. Okay, so if you take a quantum field theory in which the diagrams grow factorially because of the proliferation of Feynman diagrams, reducing to a given planarity or to a given power of n, reduces the factorial growth to a finite growth. Okay? Yes? To an exponential growth, yes? F1 of lambda, yeah. Convergent, yeah. Yeah. So, and here focus on the large limits, but thank you. Actually, all these F lambdas are convergent and with the same radius of convergence. Very important. Yes? Sorry? No, here is not the Feynman integrals. Yeah, but this is in QFT. Here we are not yet in this situation. I will come back to this in a moment. Actually, this discussion about large n is important in order to understand better what happens in quantum field theory. Because I will tell you this in a moment. Now, one way to see that this has a finite radius of convergence is to compute many terms and see how they grow. But there is actually a much clever way, and I explain it here. You can actually compute, one can compute, this is the beauty of large n, you can compute f0 of lambda exactly. And this is something that if you have never done this, you should. It's a nice exercise. It uses this Hubbard-Stratonovich trick, and this is the trick that allows you to solve vectorial models at large n. So this is a toy model of a vectorial model, but this is actually a great trick. And you can see, I mean, I wrote this, I'm not going to write the explicit expression, you can find it in the notes, but from the exact expression, you see clearly that this has a finite radius of convergence, okay? Because it's an analytic function at the origin, and then there will be branch cuts at some point, and singularities, but at the origin is analytic with a finite radius of convergence, okay? And that's actually a very important property of large n. Actually, this is the basis of many of the calculations that people do in ADS-CFT. Because actually, when you do a strong weak coupling interpolation at fixed power of n in ADS-CFT, what you're doing is taking a function that you know how to expand around lambda equals 0, and you're doing an analytic continuation to infinity. But this is very crucial that this function is convergent at the origin, is analytic at the origin. Then what you have to do is analytic continuation. A strong weak interpolation ADS-CFT is taking a function which is analytic at the origin and finding its correct analytic continuation at infinity. So the basis of this idea of a strong weak interpolation is the mathematical fact that these functions are analytic at the origin. If these functions were not analytic at the origin, then strong weak interpolation would be radically different. And all these calculations in ADS-CFT, all these successful calculations for anomalous dimensions, ABN theory, you name it, are all based on this mathematical property that at fixed order in the 1/n expansion, things are analytic. Okay? And this is a very different mathematics from what happens with divergent series. Okay? Very good. So, so actually, so this actually means that so from the point of view of singularities, of Borel singularities, what happens is the following. If you remember that the transeries is obtained by looking at the expansion on the additional saddle point, so you can see here that, remember that this was giving you this exponential 1 over 4g. So if you write it in terms of the top coupling, you see what you have here is lambda divided by 4 over n. So in units of lambda, the singularity in the Borel plane is actually at minus 1 over 4n. Okay, because you see, when you go from G to, I'm doing this just totally wrong. Sorry, this is minus n over 4 lambda, and this is minus n over 4, sorry. So from the point of view, if you instead of using the g variable, you use the n variable, you see, remember that the weight of the action is the location of the singularity. So in these units, the singularity is at minus n over 4. So when n goes to infinity, what happens to this singularity? It just goes to infinity, it disappears. But this is what you want, because what you want is that at large n, things become analytic in this 1 over n expansion. So you don't see the singularities go away. So that's actually very important, that if, so the conclusion of this, and this is a very important point, is that if the factorial divergence is due to Feynman diagrams, to growth of Feynman diagrams, Borel singularities should go away in the large n limit. So this is just saying that at large n, divergence shouldn't appear and everything should be analytic. So in particular, another way of rephrasing this conclusion is if singularity is due to an instanton, then it should go away when it goes to infinity. Okay. Okay. Very good. So very often we use quantum mechanics or even conventional integrals as giving us what we would expect in a quantum field theory. So when you summarize all this, you can actually think about what are the expectations. So from the analysis that we have done so far on basic functions, quantum mechanics, so we could actually collect some expectations for quantum field theory. What do you expect about perturbative expansion so in quantum field theory? Well, let me write a series of expectations. Yes? Mm-hmm. Yes. Right. No, again, I think, well, yeah, I would have to think about it. Yeah. Well, mathematically, phase transitions, there can be due to many things. There can be due to Stokes phenomenon in the state functions and so on. Yeah, it's slightly different. I mean, here, for example, yeah, even at large n, you see there is some sort of, there are also singularities of this function. So this function also has singularities. So usually there is I mean, what you are saying, I mean, I think what you are saying is that, yeah, at large n, you have a smooth transition from say, weak to strong coupling, but at finite n, I would expect something like more drastic, right? More, I mean, yeah, maybe yes, but yeah, I would need like a more concrete setting for this question. I mean, the question of phase transition is, as I said, you can understand phase transition as a Stokes phenomena, the fact that, you know, that that you have some sort of discontinuous behavior in your functions as you go across some sort of branch cut and so on. Okay, so in that sense, yes, you need some sort of branch cut at finite n in order to see the phase transition. But here I'm saying something very simple. I'm just saying that if you take the perturbative series and then you rearrange it in terms of the 1/n expansion, then each of these functions is convergent, and the radius of convergence is the same. This is actually the basis for double scaling limits. You know, when you do double scaling limits of large n expansions, you are assuming also implicitly that all these large n functions have the same radius of convergence. Otherwise, you wouldn't be able to do double scaling limits. Okay, so this is what happens, for example, when you want to do 2D gravity from the matrix model. You actually do this. You actually have something like this. And then you tune lambda near the common radius of convergence. You study the singular behavior of this function, and then you put it together with n. And this is the double scaling limit that gives you 2D gravity. So it's all based on this mathematical fact that this series is convergent, that this series has a singularity, but the singularities are the same for all L. Okay, so you can create a kind of coherent function, okay, out of this. Anyway, so what are the expectations for Q of t? Well, what we would expect is that the perturbative series are divergent. Are divergent due to the growth of Feynman diagrams. So this is the first expectation. So the second expectation is that factorial growth leads to Borel singularities. Leads to Borel singularities and trans series. Okay. And trans series. Physically, they are due to instantons. Okay. And the third point is that if the model admits a large n limit, factorial growth is tame to exponential growth. So we get a convergent series, and Borel singularities go away. Okay. So these are the three expectations for quantum field theory that you would expect from quantum mechanics. And I have to say that in the 1970s, people actually thought that these are true. These things are true. Okay. Now it was actually quite disturbing to see when people understood quite quickly that out of all these three expectations, there is only one which is actually true, and it is just this. Everything else is not true in general. Okay. And essentially, what happened is that you know, there was this thing which are called renormalons. And these renormalons essentially completely shattered this picture. Okay? So there was a moment in history of quantum field theory where people thought that people understood that perturbative series have limitations, that they should be promoted to trans series, but they thought that these trans series, as in quantum mechanics, would only come from instantons. Okay? But that's actually not totally not true. And in a sense, they found these renormalons, which are much more important than instantons, in order to understand the structure of other singularities of quantum field theory. And I have to say that people who come from supersymmetry and string theory are sometimes not very aware of this, and they still have a lot of faith in instantons, because in supersymmetric theories, you can tame these renormalons very much, and instantons become important again. Okay, and you can have, for example, you have n equal to supersymmetry and Mills theory. Instantons give you a lot of things, and in these theories there are no renormalons. But in a generic quantum field theory, like QCD, or not even, even an asymptotically free theory in 2 dimensions, is going to have all these renormalon effects, which essentially tell you that instantons are, if they are there, are in a sense subleading in importance. Okay, so what are these renormalons? No, the fact. Remember that that in quantum mechanics and Feynman diagrams only grow factorially. Okay, exponentially. Okay, but what people found, what people find is that there are at each loop order. This is how people found renormalons. At each loop order, there are diagrams that, after integration over momenta, grow factorially. So essentially, what happened is that. So, for example, these diagrams, examples of these diagrams, are these sort of ring or ring diagrams, which are like this. So these are this type of diagrams. So at at L loops, after integrating over Feynman diagrams, they grow already like L factorial. So what people found is that in quantum mechanics, when you do the integration, each diagram at order L only grows exponentially with L. So at order L you will find L factorial diagrams. Okay, and each of these diagrams with L only grows exponentially. But what people found is that in realistic quantum field theories you have L factorial diagrams, but then there are some special diagrams that when you calculate the Feynman integral, already this grows factorially. So it's not that you have L factorial diagrams, but there are some of them which already by themselves give you an extra L factorial. Okay. Yes, this is after renormalization. Yes. Yeah, so you want after dimensional regularization, for example, the final part that remains grows like L factorial. Okay, but this is actually I'm going to give you an example in which the integrals are finite and this is even clearer. Okay, so this is a new source of factorial growth. Sorry? Well, because in quantum mechanics, essentially, all the dependence on the momenta is kind of rational functions. So what actually gives you this type of behavior are logarithmic type of dependence on the momenta. And this logarithmic type of the momenta is typical from quantum field theories when you use, when you have running momenta, you have a running coupling constant and so on. So I don't know of any theorem that shows that this is, in quantum mechanics. Actually, there are some funny examples in quantum mechanics where you could have factorial growth. So you have to have delta potentials in quantum mechanics. It's not that delta potentials in quantum mechanics behave a little bit like if you have a quantum field theory, you have to do renormalization or so on. So for this type of potentials, you might have renormalons. Okay, but this is because they really have like a quantum field theory behavior with logarithmic. Every time you have to renormalize your coupling constant, you have some sort of running coupling constant with logarithms, you will have this type of behavior. Okay. So this gives you a new source of factorial growth, and this source of factorial growth leads to this renormalon singularity. So there will be new singularities in the Borel plane. And you see, when you think about the instanton singularities, there is this lattice structure that I was mentioning, right? That, you will have, so, for example, you have the double well. Remember that you have here singularities at, say, A to A, 3A, and so on. So actually, Parisi and Toft try to characterize and make a conjecture on the location of singularities in so I'm going to take, for simplicity, asymptotically free theories. So, so in a sense, if you have an instanton, you expect that the structure of singularities will be some sort of subset of a lattice. You will have some sort of, infinite set of singularities which are space integrally. Okay. So Parisi and Toft actually found conjecture. The conjecture of them is the following. So you have an asymptotically free theory. So you have beta 0 be the coefficient, the first coefficient of the beta function. So they actually conjecture that the possible singularities are of the form L divided by 2 beta 0, where L is a positive integer. So possible singularities in the positive real axis. There can be also singularities on the negative real axis, but they were mostly interested in the singularities in the positive real axis because these are the ones, remember, it's like in the double well, they are the ones that are going to block Borel resummation, right? If you have a positive coupling constant. So these singularities, they are also equally spaced, but in units of 1/2 beta 0. And these were, according to them, the possible singularities. This doesn't mean that all of them are going to be realized, but if there is a singularity, it must be one of these, okay? Sorry? Yeah, beta 0, I mean, here maybe I should have an absolute value, so to make sure, sometimes people have different choices of sign for beta 0. Of course, beta 0 with the standard sign asymptotically free is negative, so let's call this absolute value of beta 0, okay? And actually, this is actually quite interesting because, remember that if you have a singularity, you expect an exponentially small correction. An exponentially small correction of this here is of the form beta 0 g squared. Okay, so this would lead to this exponentially small correction. But if you use dimensional transmutation, this is actually d to the L to the d, sorry, to the L, okay? So this lambda here is the dynamically generated constant. That is a scale, sorry. And, these are called power corrections sometimes. So these are non-perturbative corrections in asymptotically free theories, and they actually conjecture that these renormallons would give actually power would be power corrections of lambda to the L. Now notice that beta 0, you have a large n variable, is going to be proportional to n. Okay, so actually you see that these sort of corrections minus L over are of the form n g squared. So these are of the form minus L over lambda. So where lambda is the Toff coupling. So you see that these exponentially small corrections survive in the Toff limit. Okay? And this is yet another difference between renormallons and instantons. Renormallon singularities and renormallon exponentially small corrections survive at large n. So this means, in particular, that in a theory with renormalons, even when you restrict yourself to the large n limit, you still get a factorial divergent series. So this miracle of large n that converts factorial divergent series in convergent series goes away when you have renormalons. So actually, this again, if you think in terms of ADS-CFT, you can see that a strong weak interpolation in an actual in a quantum field theory large n with renormalons is going to be mathematically very different from what you have in a theory with renormalons. So of course, all the theories that that have large n duals and where we can do these explicit calculations like n equal 4 super Jamils, ABJN theory, and so on, all these theories do not have renormalons because of the amount of supersymmetry. But once you have renormalons, the large n expansion is no longer a convergent series. So a strong weak interpolation is completely different story here. Yes? Yes. There are people who claim that. Okay, there are people who claim that you can use fractional instantons to account for renormalons, but the story is a little bit more complicated than this because there are models in which fractional instantons are instantons divided by n. Okay, so it turns out that sometimes the structural similarities can be a little bit more complicated, and not even fractional instantons could account for that. Okay. Yeah, unitons again these are well. Unitons, if I understand correctly, unitons have the same charge as instantons, right? So this is different. You would need to fractionalize unitons, and this is also this gives this. So there are people who claim that you can use fractional instantons to. Well, let me actually point out that the claim that fractional instantons can account for this needs fractional instantons to be realized, and this means, for example, compactifying space-time. Okay, so you would have to go. In infinite volume, this picture of fractional instantons is no conclusive. It's not clear, at least for me. Some people say that you can interpolate. You can always wish for something, right? You can always say, yeah, maybe renormalons are fractional instantons. Maybe fractional instantons only exist in finite volume, but maybe they can extend it to infinite volume. You can always wish, okay? But the question is, if you can show that this actually works or not. So to all these people who believe that renormalons come from fractional instantons, I have computed renormalon transseries very explicitly in many simple models, so they just have to reproduce them, okay, with their calculations. When they do this, I will believe them. Otherwise, it's just a wish, right? Yes. Sorry? That? No, I'm not saying this. I'm just saying that the mathematics of a strong weak. I'm making a kind of much smaller statement. I'm just saying that in a theory with renormalons, the mathematical structure of a strong weak interpolation must be much more complicated than just this analytic continuation that people have done in ADS-CFT. This is the only thing I'm saying. Huh? Yes. I don't think so. No, because you see, renormalons, as the name tells you, are intimately related to the fact you have a non-trivial renormalization group. So in Chern-Simons theories, for example, this has a running coupling constant. I don't know enough about Chern-Simons with matter. So I know about Chern-Simons in itself, where there are no renormalons. But Chern-Simons with matter, does it have a running coupling constant? I don't think so. I think once you have Chern-Simons theories, and that's the whole point, the coupling constant cannot really run, right? So, sorry, you have a one-loop shift or something like that, but that's not really a full logarithmic running. So if you don't have something like this, then I don't think renormalons will be present. Okay. So that's actually renormalons are a very interesting thing because essentially they are the new thing in quantum field theory as compared to instantons. Okay. So they are due to factorial growth in the Feynman integrals themselves. So you can have a special families of diagrams that lead you to this factorial growth, and they do not disappear at large n. So this is like a kind of diagnosis of a renormal. If you have a singularity in the Bragg plane, If it goes to infinity when n goes to infinity, then it's probably an instanton. If it doesn't, then it's probably a renormal. This is not a exact science, yes, but it's a good first, when a singularity comes to you, it's like if somebody goes to the doctor, so you have to do a first test to see how this person is doing. So the first test for a singularity in quantum theory is how it behaves with large n. If it goes to infinity, then it's definitely due to the growth of Feynman diagrams. If it doesn't go to infinity when n goes to infinity, then it must be due to some factorial growth of the Feynman integrals themselves. So this is a good first check. Okay. Now it is very difficult. It is difficult to identify renormalons. And calculate renormalons, because you see, with instantons, so with instantons we use some sort of two-lane roads in order to understand instanton singularities. We could either study the perturbative series and see where the singularities are, or we could do a direct saddle point calculation. Remember that this is what we did for the quartic integral. First, we look at the singularities by doing a careful analysis of the perturbative series. And then we said, well, let's do a saddle point calculation to match this. Okay? So you can always do a semi-classical calculation to get an idea of how an instanton works. Now, the problem with renormalons, renormalons do not have a semi-classical realization. I mean, at least some people again claim that there might be these, but so far these are claims. I haven't seen a kind of, even at the physics level of rigor, I have never seen an actual demonstration that, for example, the renormalon series that people have computed can be matched with a semi-classical calculation. I mean, if renormalons have a semi-classical realization, you should be able to do a semi-classical calculation and reproduce some of the renormalon contributions that people have computed. And as far as I know, there is no such a calculation. Sorry? No, not even in compactified space. No. Sorry? Yes, but what you have to show, first of all, you have to calculate a renormalon amplitude in this theory, and then you have to show me that the fractional instanton is going to reproduce that. Now, in compactified space, maybe there is more chances of doing this, but in infinite volume, it's definitely very hard. So, do not have, maybe I should say, a known or explicit semi-classical realization. So it's very hard to detect renormalons. So how people detect renormalons? So there are many ways of doing it. One way is, now there is another also problem with renormalons that, in these simple models, you have lots of coefficients and you can look at the singularities. But in realistic quantum field theories, you don't have that many coefficients of the perturbative series. As I said the other day to somebody who was asking me about this, the Adler function of QCD, which is one of the most important perturbative observers in QCD, there are only 5 terms known for the perturbative series. With 5 terms, it's very hard to see singularities in the Borel plane. So what people do is at large n, you can see that many quantities are dominated by precisely this type of diagrams that I was showing you here. So if you work at large n, you can actually see that many quantities are going to be saturated by diagrams of this type, and then you calculate the perturbative series at large n, you see that it's factorially divergent, and you extract the information of the renormalon at large n. So most of what is known is in some large n limit. This can be also a large number of flavors, not necessarily a large number of colors, but in some large n limit. So I have to say that when I started thinking about renormalons, I found myself very kind of confused because it seems like a very hard problem. I mean, you don't have many ways of accessing. You know that in realistic quantum field theories like QCD, QED, and so on, there are going to be renormalon singularities. The Borel plane of the periodic series will have singularities which corresponds to renormalons, but you don't know very much what to say about it. And in particular, if you want to calculate a transseries, remember that you have to actually consider the full power series that multiplies this exponential correction. So it's not so easy to see what can happen here. Okay. So what should you do? Now, in the kind of last 20 minutes I have, I'm going to tell you about some of recent developments. So when a theoretical physicist like me is shown a hard problem like this, the first thing you do is like Kim Young was saying yesterday, you try to dissect the frog, right? So you take the frog and you do something to the frog in such a way that you can dissect it, okay? So you try to get the problem in a simplified setting in which you can solve it, okay? So one way in which you can try to do this is to look at integrable models. Now, there is something very beautiful is that there are integral models which are asymptotically free. So this includes the nonlinear sigma model, Gros-Neve, and all these theories are asymptotically free. So in particular, they should have Parisi-Toft singularities. And then you can try to actually check if in these integral models you actually have this picture of renormalons and you can actually compute something. I mean, you see, integrable theories have been always like a good laboratory for theoretical physics because many of the ideas that are supposed to apply to more complicated theories should also apply to them, and here at least you can check these things. Okay, so what I'm going to give you is a kind of non-conventional example of renormalons. In a non-relativistic quantum field theory. Which is actually also surprising. So because this is a condensed matter example, and the reason we look at this is that you see there were many reasons we wanted to look at this, but renormalons, as the name comes from renormalization. So these are supposed to be things that happen in theories in which the coupling constant gets renormalized. But as I will show you, it's a slightly more general phenomenon. So when we started to think about renormalons, I said, well, what is the next thing that comes after quantum mechanics? What is the simpler thing after quantum mechanics? Well, essentially, a quantum many-body system with non-trivial interactions. So what we did is to look at an integrable model in one dimension, which is the Godin-Young model. So the Godin-Young model is a model of interacting, so delta function interacting fermions in one dimension. So the Hamiltonian is just is a many-body Hamiltonian with a standard kinetic term, and then you have a coupling constant with minor normalizations like this. So it has a two-body interaction given by a delta function. Okay. So what you want to do is to study this theory in the thermodynamic limit. So these are fermions in a circle of length L. So you want to take the thermodynamic limit, so the number of fermions goes to infinity, the size of the circle goes to infinity, and you fix the density, okay? And it turns out that the dimensionless coupling that measures the interaction is C over N, okay? So this is dimensionless coupling. And the simplest observable you can look at is the ground state energy. So you take the ground state energy of the system at finite n and L, you divide by L, so this energy density, so in the limit in which L goes to infinity and N goes to infinity. And again, this is a dimensional full quantity, but you can actually normalize it in this way. So this is dimensionless. And then what you want to do is to calculate E gamma in power series in gamma.
So this is a well-defined problem in quantum many-body theory. You have a system of interacting fermions. They interact through this coupling constant gamma, and then you can do many-body perturbation theory, and then you will get the free Fermi gas limit, which is pi squared over 12, and then there are like diagrams of quantum many-body theory. So you will get diagrams like this. You see again. So you have remember that in many-body you have like 4-body interactions of this type. So this is going to give you an interaction of this type. So you have the Hartree-Fock diagrams and so on, and you have like a very complicated perturbative series. So this is in a sense the most one of the simplest perturbation theory that I can think of beyond quantum mechanics. So this is already quantum many bodies, like non-relativistic quantum field theory. Okay. Now the story of the Godin-Young model is fascinating because people try to compute these coefficients, and in 50 years they computed 2 coefficients of this series. Okay. Okay. So this was not a lot. So at leading order. So this is a leading order. I think the sum of these two. By the way, let me say that this is 1/2 spin half fermions. Okay, so this is fermions with a standard spin. So you get here pi squared over 12 minus gamma over 2 minus gamma cube over gamma squared over 12. So there is a series here. And as I said, in the last 50 years, only 2 terms were computed, so not very much if you want to do resurgence. But then Dimitrov Volin, who was working, yes. Yeah, that's a good question. So you can consider both regimes. So that's a very good question. So in my conventions, C equals 0 is the attractive case. And C less than 0 is the repulsive case. These are my conventions. Now, the physics of these are very different. This is a very good question, and thanks for reminding. The physics of this is very different, but of course, from the point of view of the power series, it's the same thing. Okay, but I will come for this because these have very different physics, and we will see this physics here. So this series is actually, as I said, there were only a couple of terms, but then Dimitrov Volin, who was working on ADS-CFT and was interested in integrability in ADS-CFT, found a beautiful method to actually calculate power series at large orders that he applied in relativistic field theories. So we applied his method in this non-relativistic field theory, and we got 50 terms of this series. Okay, and you can see many of them in the notes. So so with 50 terms, we could actually understand what happens. So what happens is that E gamma, if you write it as CK gamma to the K, so the CK grow factorially. And this was already an important discovery, because some people thought, based on this instanton ideas for perturbation theory, people thought that if you have fermions, there will be many cancellations between Feynman diagrams. So you see there are n factorial Feynman diagrams at each order, but if there are fermions, people thought that there will be cancellations, and then this wouldn't grow really factorially. Actually, some people thought that there would be actually even a logarithmic, not logarithmic growth, something like, a much milder growth. I don't remember exactly what was the prediction, but a much milder growth as factorial. And the first thing we show is that this was clearly growing factorially. Okay. So there is this formula here, which tells you actually that there is if you look at the Borel plane, there is a singularity here at zeta. So if you look at the Borel plane of this quantity, there is a singularity at pi squared. Okay. So this is a series in quantum many-body describing interacting fermions in 1 dimension, and this leads to is a non-Borel summable series. Okay. And then we thought, what is the meaning of this non-Borel summability? What is the meaning of the singularity? Remember that we always think that singularity should be related to some physics of the problem, right? So what is the physics of this problem? And here is where this attractive case versus repulsive case is interesting. So when are you going to see the singularity? You are going to see the singularity when the coupling is positive, because this is when we are going to extract Borel's mobility. So you see the singularity in the C bigger than 0 case. So when the fermions are attractive. But what happens to a system of attracting spin-1 half fermions? Well, there is a superconducting instability. So actually, when the C is positive, which in my notation, in my conventions is the attractive case, there are Cooper pairs. And the Godin-Young model, it's known to be a toy model for a superconducting system. So if there is a superconducting system and there is a Cooper pair, there will be an energy gap, which famously, the energy gap of a superconducting system is the most important example, perhaps, or the most simple example of a non-perturbative quantity in physics. Okay? The gap of a superconducting system is actually non-perturbative in 1 over gamma. Okay? And it turns out that actually the gap here, actually remember the formula, right? So the gap here in this system is 2 pi square over gamma, so which is exactly the square of this Borel singularity. Okay, so actually this is actually sort of understandable. Because the gap is usually is related to the square of the ground state energy in a sense. So here, it's actually we made this conjecture. So this is the energy gap, which goes like this. We made this conjecture that the energy. So the singularity in the Borel plane is half of the energy gap. Okay. So of the exponent of the energy gap. So actually, this is actually very interesting because, in a sense, what is this telling you? Simply that the Borel singularity gives you the non-perturbative scale of the model. So any non-perturbative phenomenon in this model is going to be an integer power of this scale, in a sense. Okay, and this is exactly what we found here. So this is an example in quantum field theory in which you have a divergent series, which has the singularity has a very kind of physical meaning, but not really related to instantons. It's related to this energy gap. And actually, this conjecture we also check for other superconducting models, like the Hubbard model in 1 dimension. So we check it in many cases. Now the question is, you have followed this lecture of today. The question is what? Okay, this is the meaning. This is related to the energy gap of the superconducting system, which I think is a very beautiful connection between Borel singularities and non-perturbative physics. But now the question is, what is the origin of this? What is the source in perturbation theory of this? Is the number of Feynman diagrams growing very fast, or is there some renormal type of effect? So in order to decide about this, what we did is precisely to use a large N limit. So we consider fermions of spin kappa, arbitrary. So you can take the limit of large kappa. And then you can see that when you do this limit of large kappa, essentially the physics is going to be dominated by you see here there are many diagrams, but actually the physics at large kappa is dominated by ring diagrams. So dominated by this type of diagrams. And then, they give the leading Borel singularity. Okay? And this singularity does not go away as kappa goes to infinity. Okay? So it's clear that in this case, in this model, there are renormals. There is a family of diagrams that already by itself grows factorially. And one interesting thing about this is that, you see, this is a theory in which the coupling constant does not really run. I mean, gamma is a parameter. Order by order in perturbation theory, the sum of all diagrams is finite. You don't have to do renormalization, you don't have to do dimension regularization, anything. You just calculate the diagrams and sum them, and you get a finite answer. So these are renormalons. So this is a renormalon singularity in a theory in which there is no running coupling constant or anything. So this is really a very general feature of quantum physics that it might happen that perturbation theory is divergent because there are these renormalon diagrams, and then you will get a Borel singularity which is not due to an instanton configuration. Actually, it's very hard to find an instant in a pure fermionic theory like this. It's it's not so obvious what would be the instanton type of behavior that you would have. And still, you have all these renormalon diagrams, and they explain, in a sense, the non-perturbative physics of the model, which is that you have an energy gap. You have a superconducting system. So you see, sometimes people, when you study condensed matter, when you start superconductivity, people tell you, well, when you have a superconducting system, you cannot do standard perturbation theory because you are not in the normal state, you are in the superconducting state, and so on. So this actually is true, but it's not true that you cannot do perturbation theory. Of course you can do perturbation theory, conventional perturbation theory for a superconductor. What we are suggesting here is that the signal that you are in the superconducting state is that your perturbative series will be not Borel summable. So the lack of Borel summability of the perturbative series for the normal state of a superconducting system is telling you about is signaled by the Borel singularity. Okay? So the Borel singularity is the signal that your perturbation theory was done around the wrong vacuum, in a sense. Okay? But in the sense that this is similar to the double well problem, right? The double well problem, you are expanding around a perturbative vacuum, which is not the quantum vacuum. So here is somewhat similar. If you insist in doing conventional perturbation theory for a superconducting system, it's okay. You will get a perturbative series, but the price you will have to pay is that the series will not be Borel summable. Still, the singularity of the perturbative series will tell you about the physics of the superconducting system. And then, of course, what we know is that you can always try to complete your series with a transseries to remove the Borel singularity and so on, and we gave some indications that this can be done in this example. Okay, so in principle here, one can in principle construct. We actually constructed the first term of the transseries. One can in principle construct a transseries reproducing the exact answer. Sorry, what? Yes. Well, yeah. No, this is the first set of the state is separated by a exponentialism. This is like a little bit like the double well. Yes. Yes. That's a very good question. So the gap itself, for example, is multiplying a divergent series. So, and we didn't compute this. So actually, the gap, it's an interesting problem. In principle here, since this is an integral model, you should be able to compute all this, but we were not able to do it. Okay. Yes. Yes.
If you don't have a kind of instanton picture, how can you deduce the form of the frame theory?
Oh, because here, well, there are two ways of doing it. One way is by looking at the singularities of the perturbative series. You work sufficiently hard, then you can get here. But as I mentioned, this model has the property of quantum integrability. So there is an exact expression for the ground state energy as a solution of an integral equation. So you can try to extract the transseries from this integral equation. This is extremely hard mathematical problem. But we did a lot of progress in solving this problem, and this is one way in which you can try to extract the transseries. But again, here we exploited quantum integrality. But a priori, I could try to to find the trans series by looking at the singularities and finding, and trying to see if with this series I can still reconstruct the exact answer. Okay, so reconstruct a series that resumes to the exact answer. And then, and again, this let me point out, as this person asked, that this exploits integrability of the model. So integrable models are a wonderful laboratory for understanding non-perturbative physics, because you can really make statements very precise. And let me just finish my thing by saying that we did something similar for relativistic models. For relativistic asymptotically free theories, and we found counterexamples to the Parisi conjecture. So this Parisi-Topf conjecture is on the location of singularities is not probably the last word. And actually, I have to say that renormal physics is a very difficult subject, but it's a very interesting subject. And it's a subject where the foundations are not very clear. I mean, there are still many things to be understood. And we were very surprised that this Parisi-Topf conjecture, which is like almost 50 years old, was taken for granted. And then, when we did a careful calculation in integrable theories, we found that not all the singularities of these theories follow the pattern discovered by Parisi and Topf. So this was quite a shock for us. But this means essentially that we have still a lot to understand in terms of renormalons, because all the theory of renormalons, including all these speculations about semi-classical realization of renormalons, were based on the Parisi-Topf conjecture. So now, once the Parisi-Topf conjecture is no longer true always, then you have to rethink again about it. And then, it might happen, and this is a sort of negative prospect for the subject, but it might happen that the wall of exponentially small corrections, I mean, it's clear that once you do perturbation theory, there will be exponentially small corrections. And what we're trying to do is a theory of the exponentially small corrections. Resurgence is a theory of exponentially small corrections to the perturbative series. But maybe there is no really a very coherent theory, in the sense that every exponentially small correction is associated to some object that you have identified. That was the dream of instanton physics. Instantons are in one-to-one correspondence, more or less, with exponentially small corrections. So if I have exponentially small corrections, it's because I have some configuration of my fields, which is responsible for it. Renormalons were already the first backslash against this picture, because there were these kind of objects that you discover in perturbation theory, but it was not clear what do they mean from the point of view of the Feynman path integral. And then, Parisi and Topf tried to kind of make a theory of this. But now we are seeing that renormalons are, in a sense, much more generic and more wild than what we was thought. So maybe there is no theory of exponentially small corrections in which you can, in a sense, classify a priori all these exponentially small corrections in terms of some objects or in terms of some phenomena. For example, my friend Martin Lusser, who is one of the great experts in the world in lattice gauge theory, told me, I'm not sure there is such a theory of exponentially small corrections in, say, Jan Mills or QCD. I mean, maybe, you can write these exponentially small corrections for different observables, but maybe there is no such a general theory. Okay, so still things are very much open, and I think this is a great subject to work on. Okay, anyway, so let me thank you for the hospitality in Korea, and for this wonderful school, and for your interest, and for your questions, and for the great food, and the friendship. Thank you very much.
Okay, thanks a lot for the wonderful lectures. More questions, please.
Yes.
Thank you very much for wonderful lectures. This is a very speculative one. Can you have something like a doubly exponentially small corrections?
Yes,
like
that's a very good question. And people have speculated that this is the case. So there are some speculations, notably by Misha Schiffman, that you could have double exponentials. And the reason is the following. You see, when you do this resummation of the trans series, you see each term of the trans series you have to resound this phi omega, remember, right? But then it might happen that you have an infinite number of corrections to sum. So is this sum of exponentials converging or not? So if this is convergent, then it's okay. But if it's also factorially divergent, there might be another source of exponential corrections, okay? So that's actually a possibility, and people in QCD use regularly this sort of framework to try to feed the data to perturbative series. So this is so in the kind of simple examples that I have worked out, this doesn't seem to happen. But yeah, in QCD, it might happen that you have to introduce exponential of minus.
So semi-classical picture for that is even more mysterious.
That's again the thing. You know, it's not clear what is the object that should be responsible for this. But I have to say that I mean the theory of this exponential of minus exponential objects is not. I wouldn't say it's completely established. I mean, I think people play with it, but I'm not completely. I don't think there is a clear picture. Okay.
Okay, more questions, please.
Yeah, maybe questions in the chat. Yeah.
There are two questions from the online audiences. The first is that, is there a way to understand the similarity of the gap and the instanton physically as well as in Borel plane singularities?
I'm not sure if I understand the question. So is there a way of understanding physically the
Similarity of the gap and the instanton.
Oh, that's very good. That's a very good question. Yeah. Well, as I said, there are similarities in the following sense. So take the double well. Why do we think that the one qualitative way of understanding the Borel singularity of the perturbative system double well is that you are expanding around the wrong vacuum. You are expanding around this doubly degenerate vacuum that we know is not true. So in a sense, you can say the Borel singularity is the price to pay for expanding around wrong vacua. Okay, and this happens also in other examples in physics. And the singularity in the Godin-Young model seems to be of that type, in the sense that you know that the ground state of this system is a superconducting, is sort of BCS type of ground state, and you are insisting in doing conventional perturbation theory. So at the end of the day, you want to expand around the wrong vacuum, you are going to pay for it, and the way to pay for it is this lack of Borel singularity, the lack of Borel summability. So I would say that there is some parallelism, that in a sense, the Borel lack of Borel summability seems to be related very often to your insistence in expanding around the wrong vacuum. Okay, but this doesn't mean that the vacuum is unstable. Okay, in the sense of so you see the double well doesn't have an unstable vacuum, and in many cases you can cure for this lack of Borel summability by adding appropriate exponential terms. This is what we saw with the double well. So again, you know, the lack of Borel summability is not necessarily indicating an unstable vacuum. Okay.
And the second question is, if you put QFT on a finite lattice, what happens to the renormal singularities?
Yeah, that's a very good question, and I haven't thought too much about it. But I would expect that, yeah. So this is like working with a cutoff. I think I would expect still, you know, in some cases you can still have renormal singularities, because as I said, the renormalons are not really related to the fact that you are renormalizing the theory, as this kind of condensed matter example show you. So I think it could be perfectly possible that you have something like this. For example, the Hubbard model is some sort of a lattice model, right? Because you have, like, you know, you have electrons in a lattice, and you have a lattice model, and still you have renormal singularities. So I don't think this is an exception, but it's definitely much less explored than other things that we have done. Yes.
So in two-dimensional field theory, there is a sine-Gordon dual to Turing models, and there is highly non-trivial dualities.
Yes.
And what happened to, say, renormal layons or that sort of thing?
Yes. Now these are. I mean, there is a full class of integrable models which, from the point of view of quantum theory, are super renormalizable. So you can perturb them and construct perturbative series in these perturbations, or all these perturbed conformal field theories in 2 dimensions. So the physics is very different because these models are super renormalizable. So I'm not sure if models are super normalizable, you would expect only to have instanton type of singularities. Okay, so in these models, in principle, I don't expect renormalons in general. But again, these are models that should be also should be explored. And I have to say that the techniques we use for integrable, asymptotically free integrable models were much inspired by work on Sine-Gordon models. So one might be able to also look at resurgence in those type of models. All this is still very much open.
More questions? Yeah.
Sorry?
Can you apply this resurgent program to, let's say, string theory amplitude?
Yes, that's a very good question. So we actually, in a sense, my original motivation when I started working on resurgence was to actually think about the string theory. So there are various cases in which you can apply this to string theory. First of all, one thing that you can study is the convergence of the 1/n expansion itself. And you see, the 1/, I mentioned the 1/n expansion here. So each term, each function appearing in the 1/n expansion is an analytic function. But the 1/n expansion in itself should be divergent. And we know that it's going to diverge, like, say, in matrix type of models, it's going to diverge like 2G factorial. So you can actually try to understand the divergence of a string perturbation theory using resurgent techniques. And then you expect that in many cases, this is going to be due to D-brane type of instantons. Okay? And in one success story of this is actually non-critical string theory. Non-critical string theories is very easy to kind of calculate the perturbative series at 2 very large orders. For example, you take a 2-3 minimal model coupled to gravity, which was solved in the double scaling limit in the early 90s. You have the full power series of string theory, and it's a divergent series which diverges like 2G factorial, and we know that the divergence of this series can be related to D-branes in minimal strings. So this is a story in which we understand this very, very well. And one thing you can do other studies. So you use the 1/n expansion in full. You can try to understand the string perturbative series by looking at the 1/n dual. And we did this, for example, for ABEM theory. And we found evidence, again, that the free energy of ABEM theory, which is something that you can compute in much detail, is a divergent series in 1/n, which is a divergent series in the string coupling constant. And again, we found evidence that the non-perturbative effects associated to this were due to D-branes. And one model we have essentially made a lot of progress with it recently is topological string theory on Calabi-Yau's. So you take a topological string theory on a Calabi-Yau target. This also has a perturbative string expansion. And actually, we found with Jay Wu, we found all the possible instanton amplitudes for this theory. Okay, so we really have a closed form solution for all possible instanton amplitudes. Now the question is, where are going to be the Borel singularities? It's a complicated mathematical problem, but we know what is the phi omega. Remember that I introduced this phi omega set of singularities. We know the form of the phi omega for any possible singularity. So in that sense, we have made a lot of progress in understanding resurgence properties in string theory. So string theory, in a sense, it's a beautiful setup to understand resurgence because it definitely seems to be simpler, at least in the examples I have looked at, it seems to be simpler than QCD.
Okay. More questions? Okay, if not, let's thank Marcos for his wonderful lectures again.
Yeah, I think, these are sometimes, going through more basic things is very good.
Thank you. That's really wonderful.
It's a Kimil.
I guess this is his.
Okay.
And then.
Okay, and maybe I change name. And another settings. Yeah.
Should I just scroll down or?
Yes, that's right. Is it right? Scroll down or?
Or scroll, yeah, sideways, I guess.
Yeah.
Yeah. Okay. Morning. Hey.
Probably.
Oh yeah, I'll put this on. Yeah.
All right, so let's shall we resume? So so Chris will continue his lecture on quantum error correction and black holes.
Thank you. Yes, and welcome back for the last installment of this. So last time, remember that we introduced Theorem 2, which was a generalization of Theorem 1 that is supposed to hold for general code subspaces. So instead of the context of Theorem 1, which had to have these fixed QES subspaces, here we were allowed to consider more general subspaces of ADS and to talk about these more general subspaces, which we wanted to do because it's these subspaces that have typical black hole states. And Theorem 2 looked a lot like Theorem 1, but the conditions were slightly different. So again, we had this condition 1, which was some sort of reconstruction statement. And we had this condition 2, which was essentially the statement that you could compute the von Neumann entropy of your region capital B using something that looks like the quantum extremal surface formula. So the entropy of capital B equals the entropy of little b, which is the region you can reconstruct, plus some extra term that didn't depend on the state. It was this area term. So is this thing that, when applied to ADS-CFT, becomes the geometric area of the quantum extremal surface. So these two were equivalent, and we noted some peculiarities and some reasons for this peculiarities. Like it surprised me at first when figuring out this theorem that the thing you can reconstruct it's not any operator or any unitary. It's these product unitaries, and this reconstruction is guaranteed to work for a particular psi. So this U of capital B that is reconstructing this product U on little b works when acting on V psi, but not when acting on some other state. So for example, can I write it in blue here? Yeah, so if you had, if you tried to take that UB, that same one, and acted on, say, V omega, where omega is just a different ADS state, and you were asking, does this equal V acting on this state? So you took the same product unitary, this time acted it on omega instead of psi, and then acted it with V. You could ask, does this equality hold? And the answer is, in general, no. So in this sense, this reconstruction is state-specific. And also, so here, theorem 2 is guaranteeing us, theorem 2 is guaranteeing us that we can do the state-specific reconstruction of these product unitaries. So it's a slightly perhaps stranger sort of reconstruction than the one that theorem 1 gave us, and that was, in some sense, the price we paid for generalizing away from the strong assumptions of theorem 1. Today we're going to talk about, what we should think about the fact that this is guaranteeing us just state-specific reconstruction of product unitaries. We're going to see that actually that's very useful in practice, more useful than you might have thought naively. But before doing that, let's also note that another nice thing that theorem 2 gave us was this condition 3. So 1 and 2, which are equivalent, each implies this condition 3, which was this nice statement that the region little b, that was the entanglement wedge, the little b that shows up here, minimizes this area plus entropy, which is very close to this quantum extremal surface formula that we have in real ADS-CFT. Of course, the real quantum extremal surface formula in ADS-CFT has this extra extremality in the time direction, right? We say extremal instead of minimal. And that is an important point. And it is actually significant in my mind that this theorem, which is quite general, the assumptions are quite general, gets this minimality, not extremality. So it's an open question, a very important one. What is the theorem 3 you would have to write down? What are the assumptions that are different from these that would end up with a quantum extremal surface prescription? So this was one step towards getting that, but maybe not the whole way. And I'll come back to that at the very end. Yes. Okay, yes.
That means that should we first find a very special psi where, or very special class of states where this theorem is true?
Good. The way you should read this theorem is saying, in practice, what we do in ADS-CFT is we say start. So this is my time slice, and I pick my boundary region B, and I have some CFT state. Let me call it psi tilde, and it's dual to some ADS state. Let me call it psi. So I'm imagining we know what psi is, and then what we do in practice is we say, I can find the minimal quantum extremal surface. Maybe it's this guy. We'll call it gamma. And so gamma already tells us what little b is, because finding the quantum extremal surface is like, we're finding the thing that satisfies condition 2. So we picked psi, it could be anything, then we found gamma. And then now we want to ask, this theorem is telling us the answer to the question, what operators can I reconstruct in this little b?
So can I understand that then number 2 is the kind of equation which defines certain class of psi?
You might think about it that way. I would prefer to think of equation 2 of defining little b given some psi. So you pick psi first, and then it tells you what the entanglement wedge is.
So I mean, it is for me it's a little bit confusing. Why I mean for general omega it doesn't work, but for special omega of psi it works.
Sorry.
And so what is the categorization or specification of psi where it hold?
Yes, I see your question now. Yes, I said this in perhaps a confusing way. So the point is that given this other state omega and this product unitary, there would exist in general some other UB that reconstructs this product unitary. So psi has some UB that reconstructs this product unitary. Omega also does, but it's a different unitary on B. It could be a different, okay, yeah, so yes. So in general, good. This is a good discussion. So in general, let me erase these space-time pictures so I can draw another one. So let's say the bulk state is psi here. And then we have our region B on the boundary. And then in this bottom setup, we're going to consider bulk state omega. And we're going to consider the same B. So in general, in psi, say this might be the entanglement wedge. So this would be the little b for psi. Omega would have a different little b. Maybe it's this one.
Oh, okay. All right.
Yeah, and so the operators you can reconstruct in the omega case are the ones in this little b, and the operators you can reconstruct in the top case are the ones in this little b.
And also second confusion was that before you make a product, right? All those pieces, B1, B2, B3, all small pieces,
Yes.
are actually interacting each other, right? So if you release, if you form the product and then release it, then they are hopelessly entangled immediately. So how can you, make sense out of the product?
Yeah, so the states, like so psi and omega here, could be very entangled. The operators that show up here in this equation, I'm just requiring take that form of like UB1 tensor UB2, etc. So maybe one thing you're worried about is the back reaction. So in gravity, if I act some general unitary, it will back react. That's true, and that has to be taken. Into account very carefully. I think this is easiest to apply to ADS-CFT if you take some semi-classical limit, where these product unitaries are not going to back react very strongly. And then in that case, maybe it's clear. With the back reaction, it's much more subtle, but.
And also, we need to worry about the time evolution itself, because Hamiltonian will contain interaction. So
Yes.
is this at some fixed time slice?
Yeah. So this is for now at some fixed time slice. Yes, exactly.
And you don't mean that this continues to hold as time goes on, right?
Right. Yes. Well, yes. At different times, there could be a different little b associated to, right. So for psi, there might be one little b, but for e to the minus I h t psi, there could be a different little b associated to capital B. Definitely.
Thank you very much.
Yes. Good questions. Thank you for the questions. Oh yeah, so psi is not special in any sense. It's just that this theorem holds for any psi you pick. So it would hold for psi, it would hold for omega, but it's just talking about one state at a time because, for example, for psi, we might have one entanglement wedge, and for omega, we might have a different entanglement wedge. So what is little b could be different in the two states. Yes. Okay. Good. So let's address this question that this sort of reconstruction might seem very limited. Because in practice, we might want to do more than reconstruct just product unitaries in this state-specific way. And the point of this theorem is not that that's all you can do. The point is that this is just telling you how, so you can use this theorem to learn whatever stronger reconstruction is possible in various situations. Right? Because in practice, the tool that we use for learning about what you can reconstruct is the quantum extremal surface formula. And this theorem is telling you its precise reconstruction meaning. And so from this precise reconstruction meaning, you can derive other reconstruction facts that you might want if the quantum extremal surface formula implies them. So let me give you, I think, an instructive example of that. Yes? That's a great question. Yeah, so I think originally, if you asked me 4 years ago, I would have thought it holds. It's actually, yeah, there are very important counterexamples. And the main reason, the short version, is that if you look at 3, it actually doesn't depend on V. But 1 and 2 both depend on V. So in some sense, like you could pick a really bad V. That's true. That's true, yeah. Area does depend on V in that sense. It's a much weaker dependence on V than in 1 and 2. That's a good point. It's a much weaker dependence in a very sharp sense. And so you can pick pathological Vs where 1 and 2 are not satisfied, but 3 is satisfied. And that's a counterexample, yeah. Okay, so yeah, here's an example of a situation where we might want to talk about reconstruction. So here's again a time slice. B is going to be this subregion of the boundary. And let's say we have some black hole in the bulk. And also we're going to have some, well, before I say the next thing, let me say, as we mentioned before, in these black hole solutions, there are two, you can set it up, like if B is, say, 60% of the boundary, there are two competing extremal surfaces that we'll worry about. One is this guy, which we'll call gamma 1. So if this guy were the minimal quantum extremal surface, then the black hole would be in the entanglement wedge of B. And there's another one which runs like this, which we'll call gamma 2. If that were the minimal QES, then the black hole would be outside of the entanglement wedge. And we're going to talk about reconstruction in this state, actually a perturbation to the state that has some matter here. And maybe it has like a lot of matter, perhaps. But you know, let's say some order 1 amount of matter. Order 1 in G Newton. So we have a black hole and we have some matter. So the code subspace that we're considering will roughly look like this. We'll be considering different states of the black hole and also different states of the matter. Maybe it's like, maybe the matter is like some dust particles or something. It's not going to matter a whole lot. So the question that we want to ask is, you know, what operators can we reconstruct on B? And so in particular, what black hole operators and then also what matter operators. So what black hole operators can we reconstruct on B and what matter operators? And the first thing to notice is that because we have a black hole and we're taking its Hilbert space to be large, like we want the dimension of this Hilbert space to be e to the a over 4g, where a is its horizon area, and we're taking b to be 60% of the boundary circle, and in that setting, for some, say, ADS-sized black hole, the maximally entropic state of this black hole will have so much more entropy than the area of gamma 2 minus gamma 1. So in the maximally entropic state of the black hole, gamma 2 is minimal, because you want to exclude the black hole. But in a pure state of the black hole, gamma 1 is minimal, because the black hole contributes no entropy, and gamma 1 just has less area than gamma 2. That was the setting we discussed last time. And because of that, we're not in a fixed QES subspace. Different states of the black hole have different QESs. And so theorem 1 would just not apply because the code subspace is too big. So we might want to ask, what can we reconstruct? Can we apply theorem 1? The answer here is no, just because we have a black hole. But theorem 2 does apply. And we're going to see that it's going to imply that it's going to tell us some particular operators that we can reconstruct in the black hole using B. And it's also going to imply that we can reconstruct all of the operators on the matter fields. So it tells us, this good information that we just wouldn't have gotten from theorem 1 because it didn't apply. And to learn these facts, we have to look at this theorem. So this is a theorem that you can find. There might have been equivalent versions, but we proved it in this 2021 paper. And this theorem says that two conditions are equivalent. And it's going to help, this theorem combined with theorem 2 is going to help us deduce which operators are reconstructible in this example. So the first statement is that it's going to look kind of nasty. So let me summarize what it says. So it says, if you can do state-specific reconstruction of some operator for all states in your code subspace, that's condition 1. So it looks like this. For all psi on, so this is for all states in your code subspace. So all states of the bulk, including mixed states here, because we have this capital R, which could be entangled with little b and little b bar. For all of those states, and for any product unitary that you might be considering on little b, there exists some unitary on capital B such that this holds. This is the reconstruction condition. So remember, this looks a lot like the statement of theorem 1. It's very related, but what it's saying is that if there's some unitary, if for all unitaries and for all states, you can find a reconstruction, that's theorem 1. So if you can do state-specific reconstruction of these product unitaries for all states. So it's not just for one state, it's the stronger condition that you can find a reconstruction for no matter what the bulk state is. This is going to be equivalent to condition 2. Actually, I want to say this statement of 1 a little bit better, because I think that I didn't clearly communicate it. So in our example, we had this black hole, right? And we had region B, and we had these two candidate extremal surfaces. And then there was some matter here. Now the point, so theorem 2 told us that whatever the entanglement wedge of capital B is, we can do this sort of reconstruction for that psi. So if, whatever the psi of the bulk is, we're guaranteed to be able to do this for B being the entanglement wedge. But now the matter is always in the entanglement wedge. So it's always in the little b in this statement. It's only the black hole which for some states is in the entanglement wedge and for some states is not. Or maybe it's not just the black hole, it's the stuff around the black hole too. Everything between gamma 1 and gamma 2, sometimes in the entanglement wedge, sometimes not. But the matter is always in the entanglement wedge. So this matter region satisfies this condition 1 here, because it's the case that for all states, you can always do this reconstruction. Okay, I hope that's clear. Condition 2 is much easier to understand. It's basically the statement that you can just do state-independent reconstruction. So it says that for all unitaries on little b, not product unitaries, this is just any unitary, there exists some unitary on capital B such that it works for all states. And the statement looks like this again. Sorry. So this is the statement. Condition 2 is the statement that, for example, here, that if you have some unitary acting on the matter, all right, UMAT here, that you can find some unitary acting on capital B that just always implements that matter unitary regardless of what the bulk state is. This is a lot like the theorem 1 style of reconstruction, where it's state independent, doesn't care if it's psi or omega or whatnot. Okay. So this is a theorem. Maybe the general idea of it is clear. The proof, if you wanted to understand the proof, there's actually a few different ways, of course, that you can prove it. The one that we show in our appendix uses von Neumann's minimax theorem, and that helps you flip the quantifiers here. So the upshot of the theorem is that any region that's in the entanglement wedge for all states in H code can be reconstructed in a state-independent way. And good. And if you apply this theorem to this example with the black hole and the matter, what you determine is that you can't reconstruct black hole operators in a state-independent way because for some states it's not in the entanglement wedge. But you can reconstruct matter operators in a state-independent way because they are in the entanglement wedge for all states. Okay. But we're not completely out of luck for asking about what we can reconstruct in the black hole, because you can consider subspaces of the black hole state. So this is going to be an important point. Or important takeaway, although I won't use it later on. Yeah. It holds for, you can have black hole, you can have matter, yeah, you can have any bulk states you want, as long as it's always true that 1 is equivalent to 2. Yes. Here, u little b, I might be confusing people by using little b so much. Here, little b doesn't necessarily mean the entanglement wedge. It means little b here is some region of the bulk. So condition 1 and condition 2 here are satisfied in our example, for little b being the region that's between gamma 2 and capital B. If you took, so that bulk region between gamma 2 and capital B satisfies conditions 1 and 2. If you asked about the bulk region between gamma 1 and capital B, that would not satisfy either condition 1 or condition 2. Yes, good. Thank you. That was exactly what I was about to bring up. So this is an important thing you can do, is you can, instead of considering the code subspace we had, which was like the full H black hole with dimension e to the a over 4g, you could instead consider a subspace of this, where you say, like, let me just be a little bit less ambitious and consider some, I don't know, H sub, which is a subspace of this, in which the black hole has, we're going to consider fewer black hole states. We're only going to say, take like, I don't know, some order 1 number of black hole states or something. And if you, so you take some fraction of the black hole states, and if that fraction is small enough, then it can be the case that the black hole is always in the entanglement wedge for all states. Alternatively, you could, maybe this is what you're about to bring up, you could consider a larger B. So if you, like, I think for BTZ, so like 2 plus 1 dimensional black holes, if B is larger than 7/8 of the boundary, then that's sufficiently large that gamma 2 and gamma 1 have areas that are so different that an ADS-sized black hole, even if you imagined it had this many states, would just always be in the entanglement wedge. So you could do that. You could just, and that actually brings me exactly to this next point, the point that we'll discuss for the rest of this lecture. The point is the following. This is a very important point. So let's finally return to our grander questions about black holes, right? Because, you know, ultimately, we've been talking a lot about subregion reconstruction, but ultimately, what we would like to do is just understand the interiors of black holes. And maybe we don't care to use some just fraction of the boundary to do that. Maybe we'll be happy if we can understand the interiors using the whole boundary. So instead of this scenario, where like we have to worry that there's 2 extremal surfaces that might be minimal, let's take B to be the entire CFT. And then we could say gamma 1 and gamma 2, as we just said, have sufficiently different areas that we would perhaps, that even if the black hole has e to the a over 4g states for a ADS scale, the black hole will clearly be in the entanglement wedge. But there's actually, so perhaps counterintuitively, this actually doesn't work in some very important examples. So the question we want to ask is, in this case, can B just obviously do this powerful sort of reconstruction we want, this so-called state-independent reconstruction of general black hole operators? Because, you know, if yes, then we would be a long way towards answering our major questions, because right, the PETS map and these other schemes that I introduced for doing this reconstruction, those work for this theorem 1 style state-independent reconstruction. This theorem 2 style state-specific reconstruction of product unitaries is much less well understood. We don't have these closed form formulas like the PETS map to do that reconstruction. That's an interesting research goal. So we would like to be able to do state-independent reconstruction, say in this case. Can we do that? So can we just do the PETS map or something? And actually, right. So if we look at this scenario, it actually is subtle for the following reason, and this is going to be very important. So if the dimension of the black hole is less than like e to the area of the black hole over 4g, then the answer to the above line is yes. Because let's say we tried to compute in this right diagram, we tried to compute the position of the quantum extremal surface of B. And roughly speaking, there are two candidates. So I'm just redrawing the black hole a little better here. There's two candidates. Now, so one candidate is the trivial surface, so you just have no quantum extremal surface at all. And so in that case, so I'll write trivial surface. S of B by the quantum extremal surface formula is just given by the entropy of the black hole. Let's say the black hole is in its most entropic state, which is like a black hole over 4g. Sorry. Yeah. You know, if the dimension is bounded by this, then this is the most the entropy can be. And the other candidate surface would be one that actually wraps the horizon. So instead of the quantum extremal surface for B being trivial, you could consider one that wraps the horizon. But in that case, you get the same answer, because the QES formula would tell you that the entropy of B is just given by the area of the quantum extremal surface over 4g. But if the QES is wrapping the horizon of the black hole, then its area is the area of the black hole. And so these are equal. So as long as the black hole has no more states than e to the a over 4g, then we're at worst on the cusp of some phase transition where the QES of the entire boundary wants to exclude the interior. So this suggests that, okay, maybe we can feel safe that if black holes don't have more states than this in ADS, then the interior is included in the entanglement wedge of capital B, and so we can reconstruct operators in there that work for any state. But actually, this boxed assumption here is not generally going to be the case in all situations that we care about. In particular, if you have some evaporating black hole, old black holes past the page time, which I'll define momentarily, will not satisfy this. So so this might be counterintuitive to some who haven't heard this before, but even though we often want to think about black holes as these objects that physically are well described by a Hilbert space of dimension e to the a over 4g, the semi-classical description of black holes, like the one that Hawking gave, he would have described a black hole by with some geometry that has some interior, and there can be modes excited in the interior, and those modes could require a very large Hilbert space to describe. So let me say that in more detail. So the summary of what I'm trying to say is that you sort of face a naive problem with our ability to reconstruct the interior when you consider, say, evaporating black holes, which we are very interested in considering because we want to understand things like the information paradox, and this is exactly the context for the information paradox. So the idea is the following. So remember So let's imagine we have, so how do I want to draw this Penrose diagram? So you can imagine that, so instead of the usual cylinder, where this is the usual picture we would draw for ADS, and I could draw a black hole in this diagram. It's going to be more convenient for us to draw black holes. We're going to sort of flatten the cylinder, and we're going to think of this line as the asymptotic boundary where the CFT lives. So this is the boundary of the ADS, and this dashed line will be the event horizon of the black hole in ADS. So R is running like this, and time, of course, is running like this. So this is the ADS, and it has a black hole in it. And this is the singularity of the black hole. And for large ADS black holes, well, for any black hole, as time goes on, you essentially have pair production of, let me draw this in a different color. So, Hawking radiation can be roughly understood as you have these modes outside and these modes inside, and they're entangled. And this mode inside can't escape, but this mode outside does. So he, in flat space, would run off to infinity. But in ADS, he actually will hit the boundary, and often we take the ADS boundary conditions to be reflecting. And in that case, he'll reflect off and he'll fall back into the black hole. And so usually if you just have a big black hole in ADS with reflecting boundary conditions, it's stable. It won't evaporate. But I want to talk about evaporating black holes because I might be interested in flat space black holes or something. And we can mock that up in this ADS situation by changing the boundary conditions of ADS so that we let the radiation escape. So it's not reflecting, it's transmitting. And we're going to help ourselves keep track of everything by allowing it to escape, but into a reservoir that we control. So have this, let's introduce this. So this is sort of the Penrose diagram for some flat space region. And it's going to be non-gravitational. So we're so the way this diagram works is that these modes here in the ADS, so they're living in some gravitational region, they fly out to the boundary of ADS, and then the boundary conditions are such that they pass through it. And they then enter this flat space region, which is actually non-gravitational. And it's, you can make this work out consistently, and there's some great papers about this. I'll be happy to, I'll put the references in the lecture notes, but also I'll tell you if you would like to know more in person. Good, so when you construct this setup, you now have the situation where you have this black hole in ADS that is evaporating away. All of its radiation is, with time, the radiation is leaking out, and you can just ask questions like, let's look at this reservoir. We're going to call the reservoir R, say. And I can consider, say, this time slice of the reservoir and ask what its entropy is or something. And in fact, let me do this. So let me consider one big time slice. So time slice that runs through the reservoir like this and then continues into ADS. So this is some big nice slice, and it includes parts in the reservoir where the radiation outside is, and it includes parts of the interior. And as we described, all these modes out in the reservoir are entangled with excited modes, excited low energy modes in the interior. And so we're going to call the interior degrees of freedom, we'll call those, I don't know, we can call them little r, or like, I overused little b, but let me call it little r. And we'll call this stuff out here big R. Okay, so little r is entangled with big R. So this is a situation you can construct in ADS. And the point here is that as time goes on, so we've set up this black hole in ADS, we coupled it to capital R, and then we evolve with time now. And more radiation is escaping. The black hole is losing energy, it's shrinking in size, so its area is decreasing. But meanwhile, more and more modes are being, more and more low energy modes are being generated in the interior. So I didn't mean to erase. So you end up with a black hole whose area is decreasing, but from this semi-classical description of the black hole as low energy modes in the interior, those low energy modes, their Hilbert space is increasing in dimension. So there's going to be a crossover, which is called the page time, where in the semi-classical description of the black hole, there's more, the Hilbert space dimension is larger than e to the a over 4g. And what this means, okay, so let me write that down because it's very important. So eventually, so at page time, the page time. So the entropy of R is going to be, can be much greater than the area of the black hole over 4g. So that would, in our previous way of drawing the situation, that could look like the following. So we were taking capital B to be the entire CFT, and it's dual to this black hole, and then there's some like reservoir R that I'm going to draw this way. It's some circle elsewhere, and but there's a lot of modes excited inside the black hole, and there's so many that there's so many that the minimal quantum extremal surface of B is going to be the one that wraps the black hole. So the minimal quantum extremal surface of capital B is going to be this one that has generalized entropy equal to the area of the horizon over 4g. Because if it didn't wrap the horizon, it would have to contribute an amount to the entropy of B that was equal to this larger quantity, which is the S of all the interior modes, which is larger, so the minimal one wants to be the one that excludes that. Let me indicate here that R is heavily entangled with the interior modes. That's what these lines indicate. Okay, so we have this situation where even though we're allowing ourselves access to the entire CFT, and the entire CFT we imagine is dual to this black hole, it looks like we can't use the entire CFT to reconstruct operators in the black hole. And we could say, well, okay, is this really a big deal? Maybe we just, in this case, there's more stuff, and there's also this capital R. Maybe we just demand that we reconstruct interior operators using a union of capital B and capital R. And I think in some sense this is like the lore that's said. People tend to believe that this is just what you'd have to do in these cases. But this is, if I can communicate one thing to you from this lecture series, is that that's too simple. You actually can't use even the union of capital B and capital R to do state-independent reconstruction of the interior. And so let me write that down. Can't do state-independent reconstruction. So like this theorem 1 style, very nice reconstruction that we understand with the PETS map. Can't do that for the interior. Even using all of capital B, capital R. And let me try and communicate why. The short reason is that state-independent reconstruction of some operator requires that, so like, you know, you're asking, okay, we have this operator in the interior here, some phi, acting at that green dot in the interior. And we want to ask, can we find some operator that's acting on capital B, capital R, that implements that operator? And for that to be the case, one thing that we've noticed from these theorems is that that would require that the operator is in the entanglement wedge of capital B, capital R for all states. But that turns out not to be the case. It's not true, because you have to also consider states in which the interior, in which R is not even entangled with the interior. Something else is entangled with the interior. So you have to consider, let me say it this way, you have to consider all bulk states, pure and mixed. So you even have to consider states in which the degrees of freedom in the black hole are in some highly mixed state. And in that case, they're not entangled with R. And because they're so mixed, the QES of B still wants to exclude them. So in these states in which the interior is highly mixed, the entanglement wedge of B union R does not include the interior. So you can't do state-independent reconstruction of the interior even using both. So our takeaway from this is that state-independent reconstruction is too much to ask for in the interior of black holes. If we want to understand the interior, it's going to be important that we do something like this state-specific reconstruction, this kind that showed up in theorem 2. And so I would like to say that this helps us appreciate the significance of theorem 2. You know, if we hadn't seen that there was this new kind of reconstruction relevant to entanglement wedge reconstruction, we wouldn't be able to write any precise sense like this in which we can reconstruct interior operators. Okay, so that's true. So I'm just saying in a very qualitative level that state-specific reconstruction is going to be important. But there's actually, related to this, there's a deeper subtlety with this setup that I would like to turn to now. And I would say this is a subtlety that's at the forefront of modern research on quantum error correction and ADS-CFT and black holes. And that subtlety is this map, you know, whatever encoding map is encoding the ADS state into the CFT state. Yes. Yeah, great. Thanks for the question. Yeah, so Papadopoulos and Raju also discuss a kind of state-specific reconstruction that is state-dependent, I think is their language, state-dependent reconstruction. And in that sense, it is related. It is kind of different on a technical level, and I don't know if I can productively say the difference in a short amount of time. Essentially, the state-specific reconstructions that are relevant to, say, theorem 2 are defined differently. So my understanding, I tried to understand the Papadopoulos and Raju proposal in this language, and my understanding is that to do their proposal in this language, you essentially have to consider a family of encoding maps V that are different for each equilibrium state. Whereas I don't want to do that here. I want to imagine that there is just one God-given V that maps ADS states into the CFT. So it's not different for around each equilibrium state. And so fixing the V or allowing a different family of Vs to be built around each state, I think it makes for a very kind of physically different setup. And so that's the short version of the difference. That's a good question. Thank you. Okay, so I claim to you, and I'm going to define this phrase more carefully momentarily, but in the example we've just seen, if it should force us to realize that the encoding map, whatever it is, this V that in principle acts on ADS states and tells you what the dual CFT state is, it should be non-isometric, because in some sense, there's more. I'm claiming to you now that that example shows there are more ADS states than physical CFT states. So let me explain this. So recall that in isometry, V is something, so this V is now a general thing. I could use a different, I don't know, maybe K. Yeah, let me write. Some isometry, let's say K, that maps from, say, Hilbert space A to Hilbert space B, is some linear map such that K dagger K equals the identity. And if you think about it, you can prove, there's a linear algebra proof of this, that this requires that the dimension of Hilbert space B is at least as big as the dimension of the Hilbert space of A. So this is a famous linear algebra theorem. So if you find yourself in a setup where you have a linear map mapping some Hilbert space A to B, and B is less big than A, then that linear map must be non-isometric. And that's a case we find ourselves in here, because here the map was this V, right? So V is the one that maps from your ADS state to the CFT, tensored with the identity on R. So our total system, our total bulk description of the system was we had ADS and we had R, and so the total Hilbert space was ADS tensor HR. And then the CFT description was HCFT tensor HR. And so to map from the first to the second, we used this thing. So it looked like this. So I think we were using little r to denote the interior degrees of freedom. So this was the map that was implicit in the example we saw. And this H capital B is smaller than H little r, right? I mean, I don't know if I've said it in a way that convinces you yet, but there is a physical meaning to the fact that we associate a Hilbert space of e to the a over 4g to black holes. And part of that is reflected in holography with the fact that if you have a black hole of horizon area A, then the size of the subspace you need in the CFT to describe that black hole is e to the a over 4g. And so the subspace, the dimension of the Hilbert space we need in the CFT to describe the black hole is always bounded by e to the a over 4g. But clearly in the bulk, we had just seen that the bulk description uses a much larger Hilbert space. The Hilbert space needed to describe all the modes in the interior. Okay. So the sharp problem that this raises is that V has a kernel. In the sense that there's some set, because it's mapping from a larger to a smaller Hilbert space, and it's a linear map, there must be some subspace of the input that it annihilates. Which is kind of weird. What do we make of these null states of this kernel? If you in some sense want to think about semi-classical gravity as some effective description, and the CFT as the true physical description, then you would be encouraged to think about null states as somehow being unphysical, right? Because they don't show up in the CFT. That's the physical description of the system. So if you somehow were living in the bulk and found yourself in a null state, that would be sort of nonsensical, because that's sort of a non-physical state. One of these states in the kernel of V, it just doesn't seem like it has any physical significance. And so it's kind of an issue that in this example we found, V seems to be non-isometric because then it has this kernel. And we're going to have to treat that very carefully. We're going to take seriously this idea that ADS is embedded into the CFT via some linear map. That's served us well so far. And so we're going to have to take seriously that it could be non-isometric. And so we're going to have to take seriously the fact that there might be these null states and we have to decide what to do with them. And so somehow we must prevent normal bulk physics from evolving into one. I mean, this is one idea. So this is kind of the idea that that some of us ran with. So now I'm going to discuss. So now I'm discussing some ideas that came from this paper from last year by me, Netta Engelhardt, Daniel Harlow, Shreya Vardhan, and Jeff Pennington. And so we're trying to take seriously this idea that it's non-isometric and has a kernel. And we want to understand, is there any principle that we could invoke to handle the issues that naively arise with these pathological null states? And the idea is that we somehow come up with a principle that says, in the course of normal bulk evolution, you'll never detect the presence of these null states that you, say, couldn't feasibly map yourself into one. So, yeah. Good. Yeah, that's a good question. So you can actually make very rigorous the fact that you only need this subspace of size e to the a over 4g in the CFT to describe the black hole in the following way. So in these setups where you have this reservoir entangled with the black hole, in the CFT description of this, you have this reservoir entangled with the CFT, and you can look at the state you have and see the subspace in which, like, you can say, quite rigorously truncate the state of the CFT such that to a very good approximation, it just fits in the subspace of this size. So you can just confirm directly by calculation that the CFT is describing this black hole with the states in this subspace of this e to the a over 4g size. So good. So let me tell you that. Oh yes.
And what is the boundary is not supposed to encode the information of both the black hole plus radiation. Should the radiation this HR, so-called the H big R, is a what? Is this a kind of observing Hilbert space which is not belonging to boundary?
That's exactly right. Yeah, it's some auxiliary Hilbert space we're introducing. It doesn't belong to the boundary CFT.
So even in the case the radiation is coming out of the original black hole, you don't think it belongs to part of the entire bulk space?
Yeah, good. So yeah, the radiation comes out of the black hole and then exits the bulk into this auxiliary system. And there is a rigorous sense in which the information has been preserved. So the information hasn't been lost. It's still, in some sense, in BR. But the non-trivial surprising claim is that you can't do this state-independent reconstruction using BR. I don't know if that.
Why should we go in that way? I guess.
Can you say that again?
Because I couldn't really understand that something entirely that is all these phenomena is happening. If all the phenomena is happening at the ADS bulk, for example, then I thought that everything should be encoded in the boundary Hilbert space also.
Good. Yes.
But you are not following that direction, so.
Right. So this example actually challenges this previous understanding, where so this is a very important insight from these 2019 page curve papers, where they allow these black holes to evaporate into this reservoir, the auxiliary system, and then in this very quantitative sense, even though the black hole is in the ADS, its interior is not described by the boundary CFT, which is to me a very surprising, non-trivial thing. But yes, that information now can be found in the reservoir, and that's the non-trivial thing. Yes.
But if you don't attach a reservoir, suppose your ADS black hole actually evaporates, then everything should be reconstructible from the boundary, right?
That's true. Yes, that's true. That is true. Yeah.
In that case, do you I mean, can you do that with a state independent way, or you still need a state specific?
So actually, you would even there you would have issues with the state independent reconstruction of the interior, and the issue is really this. Trying to embed this semi-classical description with an interior into the CFT. So even if the radiation is still in the ADS, it's just because the interior is so big and has so many low energy modes, you can't reconstruct general operators on those low energy modes in a state independent way, if that makes sense. So returning to this non-isometric V. So we're trying to understand, is there a sort of a generalization of this previous quantum error correction story? Previously we understood the ADS is encoded into the bulk using kind of like a quantum error correcting code, and that told us some things like that we could use the PETS map to great effect. But now it seems like it has to be, in some cases, a non-isometric V. And how do we make sense of the kernel that shows up? And the proposal is essentially this. And so let me write a good number of words because it's important. So the idea is, yes, indeed, there does exist a large set of null states these are null states in the Hilbert space of effective field theory inside the black hole. And they're null states in the sense that each of them is annihilated by the holographic map. So the V here, I'm calling the holographic map. The maps to what we'll call to the fundamental degrees of freedom, or the CFT, we'll say. However, this cannot be detected by any observer who does not perform an operation of exponential complexity in the computer science sense. So this is the statement. This is in some sense the main proposal that we make in this paper that I see as the natural generalization of the entire story we've set up to this point. And to better explain what we're trying to say here, I would like to now explain what I mean by complexity and exponential complexity, and why it might make sense to have that be part of a resolution with these null states. Yeah. Good. So the island is deeply related to this kernel, but yeah, so the island I would call like a subregion of little r, or maybe all of little r, and the kernel will be a subspace of this Hilbert space. Yeah. So complexity. So I invoked this idea of exponential complexity. Let's talk about what we mean there, and then why we care about it in the context of physics. Like, this is a very computer science notion, but we're doing physics, so what's going on? So complexity, by this I mean, forget about gravity and quantum field theory for a second. Let's just talk about a context in which it's more well-defined, certainly sharper to explain. So imagine that you have n qubits, like qubit 1, 2, all the way to n. And they can be in some state, but what we want to do is we want to act some unitary on them. We have some unitary, and it outputs the qubits in a new state. We talk about the complexity of this unitary as the number of smaller unitaries that you need to build it up. They're called gates. So the idea is that, in real life, if you had a bunch of qubits, n qubits, we can't just go into our lab and just automatically implement some arbitrary unitary on them. We have smaller operations that we can do in the lab, like we can flip the state of this qubit, or we can entangle these two qubits. And by doing a lot of those things, you can build up to larger arbitrary unitaries that you want. So, in real life, you have your qubits, and you might say, try and use these fundamental smaller unitaries that you can do in your lab to build up this larger one. So you would say, maybe act some unitary entangling those first two, and then some unitary flipping the state of the second one, and then maybe some unitary on the last one, and so on. And then at the next step, implement some unitary that entangles those while flipping the state of this guy, and so on. And you have to use some number, so some number of these smaller unitaries. The smaller unitaries, we're going to just call them by their word gates, like logic gates, but in the quantum setting. And we can, for definiteness, say, let's just consider ourselves to be in a fairly powerful lab in which we have the ability to implement all 1 and 2 qubit unitaries. And so if we have some giant unitary that we want to implement on our n qubits, we have to figure out some way to build it up out of our 1 and 2 qubit unitaries. And then we can define the complexity. So the complexity is like the complexity of U. So we can, given a U, ask about its complexity, and it will be defined as the number of gates, let's say the minimum number of gates that you need to build it up. And you could say it's like the complexity of U equals, I don't know, something, some function of n. N being the number of qubits. So you usually ask about the complexity of a unitary given as a function of the number of qubits that the unitary acts on. And of course, the exact complexity depends on our choice of gate set. So, given that a choice of gate set that's all 1 and 2 qubit unitaries, the complexity could be one thing. And then if we allowed ourselves to use all 1, 2, and 3 qubit unitaries, the complexity would be a different thing, something smaller. So it has some dependence on the choice of gate set, but you can prove that it actually doesn't. It's a sort of limited dependence. So, in fact, if some unitary is exponentially complex, it'll be exponentially complex regardless of your choice of gate set. And if it's polynomially complex, it will be polynomially complex regardless of your choice of gate set. So kind of for this reason, computer scientists like this distinction between exponential complexity and polynomial complexity, because that's sharply defined even without having to specify a gate set. So that's what we'll care about. We'll be asking, we'll be distinguishing between unitaries of exponential complexity and less. And we're going to care about the complexity of unitaries because this is a rigorous sense in which it is impractical. There is a rigorous sense in which it's impractical to do anything exponentially hard. And this leads us to say, okay, maybe it's not unreasonable to conjecture that semi-classical physics has some additional regime of validity of low complexity. So the idea would be, which has roots back to some papers that were written in 2013, so this is not completely out of the blue here, but the idea would be something like, you might imagine that usually effective field theories we imagine are valid unless you try and do anything, like act on modes that are too high energy or too short wavelength. And so the idea here would be maybe there's an additional time when semi-classical gravity breaks down, some effective theory that breaks down not just if you try and do operations on wavelengths of order of the Planck length, but also if you try and do things that are too high complexity. So that matters for the sake of this proposal from the previous page here, this long paragraph, because in a rigorous sense that we can write down with some interesting models, you can construct V's that act isometrically or approximately isometrically on all simple states. So all states that are that aren't exponentially complex. And in other words, these null states that we wanted to avoid all have exponential complexity. So you don't have to worry about them as long as you're only doing simple things. So this is kind of the rough idea. And how much time is there left? 5 minutes? Okay, so that's the proposal. And given more time, what I might have done is explain how you might realize this proposal in specific models. So we can give toy models in systems of qubits in which you can define a V that is very non-isometric. It maps from a large Hilbert space to a small one, mapping from a large interior of a black hole to a small subspace of a CFT, and that nonetheless preserves the inner product between all computationally simple states. And then what you would see is that the operators that you can reconstruct are the computationally simple operators. So this is an additional restriction. So basically, it's kind of like a theorem 3, generalizing theorem 2, where now the operators that you can reconstruct are have to be computationally simple in some sense. So happy to discuss that more with people offline. Let me turn to a recap of what we've seen. Oops. So we started in the first lecture by reviewing reconstruction. What led us to the state of the art? And so fundamentally, there was the extrapolate dictionary. That's how we started, and it was limited because it allowed us to understand correlation functions of bulk operators that limited to the boundary. So nothing deep in the bulk. To fix that, there was this HKLL style reconstruction. But it was also limited because it didn't seem to quite reach all the way into, say, the interior of black holes. And then we turned to the QES formula, and we saw some theorems that told us the reconstruction relevance of the QES formula, and showed us that it actually has, in some rigorous sense, all the information about reconstruction contained in it. So there was theorem 1, which was about how the QES formula relates to reconstruction in these fixed QES subspaces. And then this told us a lot about subregion reconstruction, which led us to understand that there's a sense in which ADS is encoded into the CFT, kind of like a quantum error correcting code. So QECC, quantum error correcting code. Then we saw that there's a theorem 2, which looked at general. It was like theorem 1, but for general subspaces. Didn't have to be a subspace with a fixed QES. It told us the quantum information or reconstruction meaning of the quantum minimal surface formula more generally. And then we saw that that was great. That was about subregion reconstruction. But ultimately we want to answer questions about, say, the interiors of black holes, and we would be happy if we do that using even the entire boundary. So let's take the subregion to be the entire CFT. Does that give us everything, or are we still limited? And we saw that in fact we were still limited in some interesting settings, like evaporating black holes. And that led us to consider, so the examples, especially with evaporating black holes, led us to think about non-isometric codes and some recent proposals for how to make sense of them. So that was the recap of what we've seen, and I would say there's a lot of exciting future work to be done here. Lots of questions to be answered. So one is, how do you get the quantum extremality? So theorem 2 generalized theorem 1 in some sense, but it ended up with sort of a quantum minimal surface formula. So the entanglement wedge was this thing that minimized this area plus entropy over some time slice, and does not involve some extremality in, say, the time direction. How do you get a theorem 3 that includes that extremality in the time direction? It's a little puzzling to me, and that's something I'm very interested in. There's a few others, like, for example, a lot of these, like the non-isometric code models and theorem 1 and theorem 2, they apply to these finite dimensional systems with, say, code subspaces or theories in the bulk that are, that are finite dimensional, maybe thought best of as qubits, Theorem 1 has been generalized to the infinite von Neumann algebra case. Theorem 2, I think people are working on that, but in both cases, it's kind of like Theorem 1 and Theorem 2 apply for bulks that are quantum field theories at best, not full gravitational theories. So it would be nice to better understand how gravity itself plays into these theories, these theorems. So let me say it this way. It would be nice to have more properly gravity-like, with Einstein's equation, bulk theories, say in these codes, and especially the non-isometric codes. And finally, I mentioned this in passing, but this type of reconstruction that we're promised to be able to do from Theorem 1, so given the assumptions of Theorem 1, you can do a certain strong state-independent reconstruction of the entanglement wedge. And there's even schemes for doing that, like the PETS map. But for the state-specific, weaker sort of reconstruction that you're guaranteed to be able to do from Theorem 2, there's not a closed form known for that, a closed form reconstruction formula known for that. So you might ask, can anyone think of an explicit state-specific reconstruction formula, like PETS, like the PETS map for the state-independent reconstruction? And yeah, with this recap and this future work, that is all I have for you. So thanks for your attention and the good questions. Appreciate it.
Thank you very much for a very wonderful talk. So now it's time for questions. Yes?
How important is this assumption that this, well, in the picture of the evaporating black hole, is this completely non-dynamical flat region? So if you actually have, I mean, you want to look at a black hole evaporating in asymptotically flat space-time, I guess? So you want dynamical gravity past this ADS boundary. So how important is that assumption that you just have? Yeah, good. So yeah, in this reservoir, it's some asymptotically flat, non-dynamic, the geometry is not dynamical. It's some quantum field theory, but yeah, it's important for being able, like the calculations to the level of rigor that they've been done did use that, say in the step where they just defined the region of R that they were computing the entropy of. There have been some attempts to do this in just asymptotically flat gravitating spacetimes, and the expectation is that somehow this limits to the previous the other setting with the non-gravitating reservoir. The idea being that when the radiation is going to infinity, it's very spread out, and the back reaction is very small in this limit. That said, this actually, I think, is, I would call it a controversy. There's this holography of information program that would speculate that in this asymptotically flat gravitating situation, the situation is completely different from this situation I drew here with the non-gravitating flat region. They would say that that program would say that there's no meaningful page curve, or any sense in which you could define a page curve, or like the entropy of the radiation is increasing and then decreasing with time, would be sort of ad hoc or artificial. So they want to say it's completely different in the two cases. And I'm not sure that I would agree with that upshot, but I'd be happy to talk about that more afterward. Yeah.
There is two related questions from online audience. The first one is, how is your argument of non-isometric code consistent with Haydn-Preskill result, where information can be taken out very fast and seemingly non-complex?
Yeah, good. So yeah, it plays very nicely with the Hayden-Preskel result where, so just to remind everyone, the Hayden-Preskel result is this idea that, let's say you have an old black hole, and old in the sense that it's past the page time, and Bob over there has all the radiation that's already come out. And then Alice throws in a diary that she wants to destroy into the black hole, thinking that Bob won't be able to recover it. But in fact, after a couple more quanta come out of the black hole, Bob collects those, combines them with his previously collected radiation. He can do some operation on it to decode out Alice's qubit. So in this case, actually, the operation that Bob has to do is very complicated. And so that meshes very well with this proposal, the non-isometric codes proposal, because in the semi-classical description, Alice's diary is in the interior. It's not in the radiation. Whereas the Hayden-Preskel decoding procedure is using the radiation to learn the information. So clearly, from that perspective, diary is in the radiation now. So these two completely different views of where the information is are consistent because you have to do this exponentially complicated operation to pull out, to use the radiation to figure out Alice's diary. And in our language, that's breaking the semi-classical description of the setup.
Okay, and the second question was, if throwing diary into black hole turns it to exponentially complex, can we use black hole in a reverse way, that is, bringing another white hole as a kind of oracle to achieve non-simple operations, since black hole may know what will be exponentially complex in its interior?
If we could make that idea more concrete or sharper, maybe it's sharp, but I didn't fully understand it. If we could make that very sharp, that would be exciting. There is some work by people like Bulin, Pfefferman, Vazirani, and Leonard Susskind that are doing things like this, where basically considering these black hole setups where you can learn a surprisingly complicated thing by using the black hole in a so for example, in Lenny Suskind's setup, he ends up constructing an observer who can dive into a black hole and learn the answer to an exponentially complicated question. And that is it's a very interesting setup and actually plays well with this non-isometric code stuff. But I'd be interested if the questioner wants to send me a more sharp proposal for what they have in mind. I would be interested.
So you talked about the QECC in a toy model, but what would be the corresponding statement for full ADS bulk without proving anything?
The corresponding statement to what?
For what is a quantum error correcting code in ADS, in full ADS?
Good. Okay, yes. So what I would like is to be able to write down some V, some like honest to God matrix that is able to map you from some ADS state written in some basis, maybe the Fock basis or something, to the CFT state. So yeah, to me, we will have written down the error correcting code in a very useful way if we can write down this V. And that's a challenging prospect, but people are making headway recently in the context of JT gravity and SYK. So Henry Lin, for example, has this paper where he explicitly writes down this holographic map embedding JT into SYK. I don't fully understand his, he writes it down sort of in principle. It's this, infinite by infinite matrix, so it's a little bit difficult to work with. And as far as I understand, it kind of is most well defined in some n to infinity limit. And so it's not something that would work, say, for some finite n CFT or finite n SYK. Having something like that would be the dream. If we had that, then I would say that's the code.
So it can be understood as some special V.
Yes, if we could, I think all ADS-CFT dualities, like type 2B string theory or its low energy limit, and how that relates to n equals 4 super Yang mills. There is some V that no one's written down that could rightly be called the quantum error correcting code, and finding that I think is an important goal.
I see. Can I ask one more?
Oh yeah.
So is there any case where your QES formula second part SB was calculated without any kind of a conjecture or assumptions?
Good, that's a good question. So in these, I think the most impressive calculation was this one done in 2019 by Almeri, Maxfield, Meroff, and Engelhardt. And they compute it in JT gravity. And they do assume, they make some level of, so they have some CFT in the bulk, and they have some controlled approximation. So it's impressive because it is a full-fledged quantum field theory that they're computing this S of B in for a very non-trivial region. I'm not sure if this qualifies as no assumptions, but it was certainly surprising to me that they could compute it in this case. Yeah.
Okay. So we had many questions. So let's stop here and let's thank Chris for giving this wonderful series of lectures.
Thank you.
So any announcement from the organizer?
Thank you, Chris. Okay, so maybe you heard that some of people have COVID, and some of them stay in hotel, some of them went home. So here is it's very difficult situation, and so it's rough guide, which I'll say again, that if you are from Korea, whether you are Korean or whoever from outside, but if your residence is in Korea and if you have a symptom, then please let us know and don't come to and whoever, if you feel the symptom, then don't come to the school, because there are Indian students who has to go back to India and they have to test the PCR test. Otherwise, they'll get stuck in Korea. And also, if you are from Japan, also if you didn't have 3 vaccination, then you have to have a test. Okay, so otherwise they cannot go back to Japan. So this is somewhat serious situation. So we have some test kits outside, and so if you are from overseas and you have to go back and also you feel the symptom, then you want to make sure that you are not infected. I mean, if you feel symptom, then you can stay, but in hotel. But if you feel like you want to come back, then please do get a test kit and test it. And you have to do proper testing. Otherwise, usually, if you don't put it into proper, then you get negative. So you feel like, oh yeah, I'm not infected. But most of the time, you get infected. So this. I know most of you guys probably has antibodies, so probably symptoms not that strong. But for the sake of our colleagues from Japan and India, please keep that in mind, okay? All right, thank you. Test kit outside, not many of them, but so only when you feel strongly about need for that, get the test kit and test it. But anybody from Korea, please don't. You can always have a place to go back. So just let us know, whatever. Yeah. Okay. Thank you. 내가 가져갈 테니까. 요건 나. 학교 그럼 그 레이저 여기 그 just keep